Hey everyone, welcome back to the channel. In this video, we're going to be going through rates of change, and specifically we're going to go over the difference between an average rate of change and an instantaneous rate of change. By the end of this video, you'll understand the relationship between displacement or position as it relates to velocity and acceleration, and we'll go through multiple example problems to ensure we know and can apply the difference between average rate of change, or AROC, and instantaneous rate of change, or IROC. If you guys get some value out of this video, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. Alright, let's get started. So it's a good time to talk about kind of the difference between average rate of change and instantaneous rate of change. So when we say rate of change, we're really referring to the slope. We're referring to the slope of the tangent line or the secant line. More specifically, if we look at the slope of AROC, or average rate of change, that's actually the secant line slope. And the only difference between the secant line and the tangent line is this limit here. So in this case, we're taking the limit as h goes to 0 of this whole term here. But when we're doing the secant line, or the average rate of change, we're not actually taking the limit as h goes to 0. So that's the main difference between average and instantaneous rate of change. So we could talk about, they could say things like the slope, the rate of change, the derivative, all those really mean the same thing, and we're taking that slope of the tangent line or the slope of the secant line in case of average rate of change versus instantaneous rate of change. So now if we talk about the position function, acceleration function, so we could say the position or displacement function, and we can now kind of relate that to the velocity function and the acceleration function. If you take the derivative with respect to time of a position function, or again, we take the average rate of change, or we find the slope of the position function, what we're going to get is the velocity function. So that's the slope of the position function, again, the derivative of a position function, the IROC or AROC at a certain time. So they might say, what is the instantaneous rate of change at time is equal to 3? And that, again, is you're finding the slope, but you're finding the slope value at 3. So that's kind of the difference between when we could find the derivative, which is a general derivative of the position vector or position function, or we could find a value, so a certain time of the IROC or AROC. Next, we have the acceleration function. And again, this is very similar to the velocity function and position function relationship, but we're just taking the slope or the derivative of the velocity function. That's going to get us the acceleration function. Again, it's the derivative of the velocity function, and again, we could say that the IROC or AROC at a certain time of the velocity function. So it could just say find the instantaneous rate of change at all times during the velocity function, and that would be the acceleration function at any time. But if we give a specific time or a certain value, then we're actually finding one number, or finding the value of that. Okay, so now we're doing our first example problem. And it says a medicine is administered to a patient. The amount of medicine m in milligrams in 1 milliliter of patient's blood t hours after the injection is modeled by this function. And it's m of t is equal to negative 1/3 t squared plus t, and that only exists between 0 and 3 hours. They say find the rate of change in the amount m 2 hours after injection. So again, this is when we're finding the slope, the rate of change, or the derivative, and then we're applying a certain time value of t equal to 2 hours and finding that rate of change. So what we're going to do is, let's find the instantaneous rate of change at that point. So we're going to apply the difference quotient, which is a plus h, or a function of a plus h, minus f of a divided by h, and we're taking the limit as h goes to 0. So to do this of this function, wherever we see a t, we're just going to add an h. So we're going to have negative 1 over 3, and this will be t plus h squared plus, and then t plus h again, minus the original function. So this will be minus, I'll do big brackets so I don't forget to distribute the negative here. This is going to be t squared plus t, and then this is all over h, and of course we're taking the limit as h goes to 0. So what I'm going to do now is I'm going to expand each of these brackets and expand this negative here. So first we have negative 1 over 3, and this is a perfect square positive trinomial, so that's going to be t squared plus 2th plus h squared, and then this will just be plus t plus h. Now if I distribute this negative in, it's going to be plus 1 over 3 t squared minus t, and this is still all over h, and of course we're taking the limit as h goes to 0. Next, I'm just going to expand this negative 1 over 3 into these brackets here, so this is going to be negative 1 over 3t squared minus 2 over 3th minus 1 over 3h squared. And then now we'll be able to collect like terms because everything is now added together. And this is still all over h. We can't forget that. That is still the limit as h goes to 0. So now what we're going to look for is we're going to look for different areas or different ways we can cancel these or make this more simple. So negative 1/3 t squared and 1/3 t squared positive, those will cancel. Those will sum to 0. We also have, let's see, we also have this positive t and this negative t, so that's going to cancel there. And now if we rewrite this function, negative 2 over 3 th minus 1 over 3 h squared plus h, we now see that there's actually a common term in the numerator here, and that common term is this h. Each one of these values has an h term in it, so I'm going to factor that out. So it's going to be negative 2 over 3t minus 1 over 3h plus 1. This is all divided by h. So now I think you can see that the top and the bottom part of this expression will cancel. So the h's can now cancel, and we can now sub in h is equal to 0 because now it's not in the denominator. We've actually canceled it out. So now we can actually put h is equal to 0 and have the function still be defined. So what we're going to do is we're going to sub in h is equal to 0 wherever we see that. So in this case, the instantaneous rate of change, I'll say the IROC of this function is negative 2 over 3t, and then it's plus 1, because this term, 1/3 times 0 is just going to be 0. And now they're saying IROC, or the instantaneous rate of change, at 2 hours. So if I do now at 2 hours, well, this is going to be negative 2 over 3 multiplied by 2 plus 1. So this is going to be negative 4 over 3 plus 1. We're going to get negative 1 over 3. And the reason it's negative is the function, or the original equation, gave this the amount of medicine in a patient's blood. So at first when you first administer the medicine, there's going to be a high, amount of medicine in the patient's blood, but that's going to decrease over time. So that's why it's negative. The instantaneous rate of change, or the slope of this, it's decreasing as time goes on. And that's what that negative value really means. Okay, now we're moving on to example problem number 2. And this is saying a manufacturer of soccer balls finds that the profit from the sale of x balls per week is given by p of x is equal to 160x minus x squared, and that's in dollars. It says find the profit on the sale of 40 soccer balls per week. So all we have to do there is we actually just have to sub in 40. So we're just going to say 160 times 40 minus 40 squared. If we sub that in, we will get the answer for A. So this is going to be 160 times 40 minus 40 squared. So this is going to be $4,800, and that would be the answer to part A. But now it says find the rate of change for part B in profit at the production level of 40 balls per week. So now we're not trying to find the profit, but we're trying to find the change in the profit at 40 balls per week. So again, we're taking the IROC, or the instantaneous rate of change, of this function and subbing a value of 40 in. That's going to give us the slope value and how fast it's changing at that point. So to do that, we're going to use first principles, or the definition of a derivative. And of course, this is at the function of a plus h minus the function of a divided by h. And we're taking the limit as h goes to 0. So here, I look at this function and I sub in an x plus h wherever I see an x. So the limit as h goes to 0 is going to be this is going to be 160 times x plus h minus x plus h squared minus the original function. So this will be 160x minus x squared. And this is all over h as we take the limit as h goes to 0. So similar to the last example, I'm going to expand this out. So this is going to be 160x plus 160h minus, and this is going to be x squared minus 2hx minus h squared. And then I'm running out of room, but I'll just write it below. Minus 160x plus x squared. This is now all over h. And again, we're going to look for things that cancel, and then we're going to try and factor out an h so we can divide the numerator and the denominator by h. So let's see. Well, this one here, I actually made a mistake here. This should be 160h. So that's 160h actually. And what we're going to see is, well, we have an x squared, a positive x squared, and a negative x squared. So those will cancel. Those will be summed to 0. We also have 160x minus 160x. So those will also cancel. that looks to be it. And what I'm going to do is I'm going to sub out an h, or factor out an h, of the remaining terms. So this is going to be 160 minus 2x minus h, and that's all over h, and of course we're taking the limit as h goes to 0. So now what I can do is I can cancel out this h on top, sub in an h value of 0 to the remaining terms, because again we don't have that h in the denominator. And what I'm going to get is the instantaneous rate of change of this profit function of soccer balls is 160 minus 2x. Now, if I plug in a value of 40, that will get me the slope, or the rate of change at that point in time in the profit function. So this is how many, it's going to be the amount of dollars in profit and how fast it's changing per 40 balls of soccer balls. So 160 minus, and this is going to be 2 times 40, so that's 80. So we're going to get a value of 80. So that would be the IROC of profit at, and it's going to be at 40 soccer balls. And that is problem 2. So moving on to our last problem, you can kind of see the similarities in each of these problems. And all it is we're finding the slope using first principles, or the definition of derivative, or the quotient, or the difference quotient. So here it says a man drops a penny from the top of a 500-meter tall building. After t seconds, the penny has fallen a distance of s meters, where s of t is equal to 500 minus 5t squared, in between the range of 0 and 10 for t. It says determine the average velocity between 1 second and 5 seconds. So this is where we're going to use the AROC. Before we've been using the IROC, and the only difference, if we scroll up, the only difference between that is we're not taking the limit as h goes to 0 for the AROC. We're just doing the exact same equation, but not the limit anymore. And I can show you kind of in this question how this ends up just being h on the bottom here, but let's go through that. So if I write the formula here for problem 3, the average rate of change is really just the slope. So we could say the change in y divided by the change in x. So in this case, it's going to be, we would say, the function s of t plus h minus s of t. And this plus h is the distance that the function is going. So in this case, we would do between 1 second and 5 seconds. And then divided by, we would have, well, this would be t plus h minus t. And that's why we, like this positive t and this minus t are going to cancel. So that's why we end up just getting t plus h minus s of t all over h, because these two terms here cancel out. And this would be the definition of the average rate of change. And you could probably see some similarities. If we talk about slope, or the slope of a line, what we're really doing is we're doing y2 minus y1 divided by x2 minus x1. And that's exactly what we did up here. It's the exact same thing. We just kind of expressed it in terms of f of x as opposed to y. So now in this function, what we're going to do is we're going to say, okay, well, we want the function s of 5, and we want the value for s of 1. So if we plug in 5, this is going to be 5 times 5 squared. So all this together would be 5 cubed. That's 125. So now we're going to have 500 minus 125. So we get a value of 375. Now what we have is we need to find s of 1. So now this is going to be 500 minus 5. So this is going to be 495. And now we can just find the average rate of change. So we can say AROC between these values is going to be, well, it's going to be 375 minus 495, well, and then divided by x2 minus x1. So that's going to be 5 minus 1. So AROC is going to equal 375 minus 495 divided by 4. This is negative 30. And in this case, since it's meters and we're taking the slope, our y value is in meters, right, because that's our function. We're saying s is in meters. And then our x value is in t, so that's going to be seconds. So it's meters per second. That would be our velocity, or our average rate of change of the position vector between 1 and 5 seconds. Moving on to b, we actually do the same exact process, but now with different values. So now if I do s of 9, and we need s of 9 and s of 5. So in this case, I already have s of 5. I already know that's 375. S of 9, so I'm going to put 9 squared, and then that's going to be times 5. So 5 times 9 squared. So we get 405, and then we're going to do 500 minus 405. So I'm literally just plugging in values to this. So we get 95. So now our AROC is going to be equal to it's going to be equal to 95, because this is the second, or the y2 value now, minus 375 divided by, and this is going to be 9 minus 5. So our AROC in between these values is going to be 95 minus 375 divided by 4. This is negative 70 meters per second. And that is the answer to part B. So now moving on to part C. And part C said the instantaneous velocity when t is equal to 5. So again, it said velocity, and we already had the position or displacement vector, so we know the velocity is really just the rate of change, the slope, or the derivative of a position function. But here it's instantaneous, and that's the difference. So AROC and IROC, we're kind of going back and forth between these two. So IROC, it's the same equation, but what we're going to do is take the limit as h goes to 0. So the IROC equation is, I'll do colon, limit as h goes to 0, and as f of x plus h minus f of x over h. And this again comes from the slope, but now we're finding the slope of the tangent line as opposed to the secant line, because that's what AROC was, is the secant line. The tangent line is IROC, it's an instantaneous rate. It's taking the limit as h goes to 0. So in this case, we're going to do the limit as h goes to 0 of this function. So we're going to say 500 minus 5t plus h squared, and then minus the entire function. So this is going to be minus, I'll put brackets again so I don't forget to distribute the negative, minus 5t squared, and this is all over h here. So just like last time, what I'm going to do here is I'm going to expand out these brackets. So again, we'll have always the limit, always remember this, if we forget this limit as h goes to 0, marks might be taken off. So 500, and I'm going to expand all this, this is going to be 5t squared, and then this will be minus 10th minus 5h squared, and then I'm just going to expand this negative, so negative 500 plus 5t squared divided by h here. Now we're going to look for things that cancel, so this 500 and this 500 will cancel, negative 5t squared and 5t squared will cancel, and now we'll have the remaining terms here both have an h value in it, so I can factor that h value out. This is going to be negative 10t minus 5h, and over h limit as h goes to 0. Now I can cancel these two out and plug this limit value of h is equal to 0 into this function. So this is now going to result in negative 10t. And this is the IROC of the entire function, right? So we could put in any value of time here, and well, obviously between 0 and 10 seconds, because that's where this function is defined. But if we do that, then we'll get a value of the slope at that point. We wanted the IROC, the instantaneous velocity, when t is equal to 5. So now all we need to do is plug in t is equal to 5 seconds. So we can say the IROC at t is equal to 5 seconds is negative 50 meters per second. And that would be our answer for part C. Alright, so I hope you guys got some value out of this video. If you did, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. If you guys have any thoughts or comments on what you guys want me to do next, let me know down in the comments below. Thanks again, and I'll see you guys in the next video.